right, so we are going to continue talking about vectors here. In the previous demonstration, you guys hopefully played with something that looked like this global map and saw a whole bunch of vectors sort of coming into play and a really nice use of vectors. From this map, we can see pretty easily that today, up off the coast of the northeastern United States, there's a lot of stuff going on up here, which apparently you guys, there we go. A lot of stuff going on up here. It looks very tumultuous. There's probably some sort of storm. You could say the same thing is going on down here near Antarctica. Whereas off the coast of Chile, northern Chile especially, right down here, there's not much going on at all. Obviously the colors are coming into play, but more than that, the length of the vectors and the direction of the vectors is what tells us what's going on. That is the main purpose of vectors. We want to figure out how strong is something and in what direction is it going. It's very easy to tell that the wind, generally speaking, is heading across the Atlantic from east to west, for instance. So if we talk about vectors, one of the big things that vectors tell us is a direction. All right? Which way is the wind blowing in this case? They can also tell us a speed, or maybe it's not wind speed. Maybe it's a weight of something. Something that's heavier might have a longer vector. The length of something, how strong of a force is something exerting, what the temperature of something is, etc. There's lots of different things that vectors can represent depending on the context. And so what we do is we say all of these, regardless of the particular unit or context, are some big fancy word called the magnitude of a vector. And basically magnitude is just a fancy way of saying the length of the vector. All right? So those are the two main things that a vector demonstrates: the magnitude of the length of something and the direction that it's going. If we then move on to some more formal definitions of a vector, you can see that we've got the parenthesis xy, which is a point, versus this new symbolism. Here's some new symbolism for us up here that is also an xy coordinate, but it's got those funny arrow brackets on the end. All right. So let's talk about that. If we have the point 4, 3, then that's just this place right here. That's a dot. That is simply one exact location, 4, 3. But if we add these new brackets on the end of it, these pointy brackets, then what we have is a vector which still has an x and a y, but it talks about how far we've gone. So we've gone 4 units in the x direction. So if I start here at the origin, I go 4 units in the x direction, and then I go 3 units in the y direction, then what I have is a vector. All right? So that would be a vector, and I could call this vector, for instance, A. And notice that the A has that little vector symbol over the top, and so I can say there's A. So vector A starts at the origin, and it goes out to the point 4, 3. And so it is now a vector. It's got an x part or component and a y part or component. And we've got a vector. I could also write, if I want, let's just go ahead and make a vector B. And this vector B will be the vector -2, 5. And so if I go over here, I can create that vector, -2, 5. And again, I'll leave here and I'll go -2 in the x direction and 5 in the y direction. And there I've got a vector B. Or if I want to get silly and make one more vector, then I can have a vector C, which is, let's say it is the vector 4, -4. That means the x component of this vector is 4, and the y component of this vector is -4. So it would be this vector here that's going to 4, -4. And we have called this thing vector C. All right. Now, in the previous slide, we talked about vectors demonstrating both a magnitude and a direction. So in this case, we're going to talk about magnitude being length. And so if we look at our blue situation over here, our vector A, I might say, how long is that vector? All right, now we have dealt with right triangles. This blue triangle is a right triangle for a long time. We know that x has a length of 4 and that y has a length of 3. And so, my God, how are we going to find the length of the hypotenuse of this thing? Well, that's going to just be simply the, wait for it, Pythagorean theorem. Hopefully that ran through your head. There we go, a squared. And if we work this out, 9 plus 16 is a squared, so 25 is a squared, and it turns out that, here's some new funny symbolism here for you guys. The magnitude of vector A is 5. It looks kind of like an absolute value symbol. And you can think of it as being an absolute value symbol because we think of lengths as being positive numbers. So, the length or magnitude, and that's what this means here. This means magnitude. So the magnitude of vector A is 5 units long. Won't waste your time with finding the length or magnitude of vector B and C, but we again could draw in, if we want to, that's 2 units long, and that's 5 units long, and we could again do the Pythagorean theorem to find the length of vector B, or the magnitude of vector B. Now, the last thing that a vector demonstrates is the direction. And when we're talking about the direction, I will again use our blue example over here. When we talk about the direction, it's very similar to when we had the unit circle. And if we have a unit circle here, this is of course a 5-unit circle, but nonetheless, we started with 0 degrees over here, and then we went up to 90 degrees and 180, etc., 270 being down here. And so the direction that these vectors go coincide to what angle they are as we go around the circle. So when we're talking about the direction of our blue vector A, what we're talking about is that angle measured right there. Theta. How big is angle theta? So let me just recreate a simple drawing here. Here's my vector A. Here's 3 units, and here's 4 units, and I'm trying to find theta. Now, this looks like a nice little SOHCAHTOA problem. 3 being the opposite side, 4 being the adjacent side. And so I can say the tangent of theta is opposite divided by adjacent. To get tangent, to get theta all by itself, I'm going to do the inverse tangent on both sides. And what I'll be left with is theta is the inverse tangent of 3 over 4. And if I ask my calculator what that is, I'm going to get 16.26 degrees. And so that would be the direction that my vector is heading in. It's heading in the direction of 16.26 degrees. You know what, I better check that number, but I'm fairly certain that's correct, 16.26. So with that in mind, let's try a quick example problem. So we have this vector, a vector v, which has an x component of -5 and a y component of 12. All right. So let me just draw. The first thing it says is to draw a picture. I'll try to be as accurate as I can. And I'm going -5 units in the x direction. So maybe right here I'll say is -5. And I'm going 12 units in the y direction. So maybe I'll say way up here is 12. And so if my vector is going to go -5 in the x direction and then 12 in the y direction, that means that this is my vector right here. And this would be our vector v, we're calling it. All right. So I've done part A. Sorry, I have not done yet part A. Let me quickly write that. Writing it in component form would be simply writing it like that. Okay. Now I have already completed part B. Next, we're going to try to find the magnitude. All right, well, I know that this is 5 units in the negative direction. and I know that this is 12 units. And so to find the solution to this, I can say, okay, negative 5 squared plus 12 squared equals the magnitude of vector v squared. So I get 25 plus 144 is going to be the magnitude of v squared. So 169 is the magnitude of v squared. And if I take the square root on both sides, then what I'll end up with is the magnitude of my vector v is 13. So this is 13 units long. Lastly, we want to find the direction. And remember that the direction is going to be coming from way over here. So our last answer has to be that. Okay, well, let's take a look here. The alternative would be, of course, to find this angle right here. Maybe it's a little bit easier to think about that. And then subtract to get our blue angle. So let's do it that way. We've got a triangle that's here with sides of 5 and 12. And here is the angle that we're looking for. 12 would be the opposite side. 5 is the adjacent side. And so again, we're going to use tangent. So the tangent of theta will be the opposite divided by the adjacent. Again, we're going to have to use the tangent inverse on both sides. And what we'll end up with is that theta is the tangent inverse of 12 over 5, or that theta happens to be 67.4 degrees. Okay, well that means that this angle here is 67.4 degrees. And if we subtract that from 180, what we will get is that the actual direction that our vector is heading in is, I believe if I do this in my head, 112.6 degrees. So that would be the actual direction that our vector is heading. Again, that would be using 0 degrees as a reference, 90 degrees, etc. That means that this place right here is 112.6 degrees from the positive x-axis. So with that in mind, go ahead and try the example problems that follow.